Okay, good morning. Thank you for coming, for being here today. As Andret said, now we are going to introduce a new topic in the models, which is the network. Yesterday we explained that we generate power in the generators. We have consumption in the loads, either industrial or domestic, residentials. But we need a physical mean to transmit that power from the generators to the consumers. And this is why we have the network, which is the backbone of electric power systems. You know that we have different levels of voltage in the networks. We have the high voltage that you can see when you are driving, the towers. And then we have low voltage at the distribution grids in order to have available electric supply here in the outlet, right? So here we're going to have a few volts, otherwise it would be very dangerous. Okay. Today I need to explain some topics, or I need to talk about some topics that are for electrical engineers. I know that not everybody of you is an electrical engineer, so the purpose of the next slides is not for you to be an electrical engineer, but at least not to get confused when we say something like angles in the nodes. I mean, what is the angle? What is the phase of a voltage in a node? Okay. How many? Just to know, as you have different backgrounds, how many of you is aware that the voltages that we have in the network in every node is a sinusoidal wave? Most, okay. That's yeah. Well, these sinusoidal waves can be modeled by what we call phasors. How many of you know what a phasor is? Okay. Okay, a phasor is like an imaginary number, okay, that is rotating at the same frequency as the grid. And all these phasors that are rotating, if you have let's say a snapshot, you could compare what is the angle of these imaginary numbers with respect to a given reference. So this is why we need to establish an angle reference in the network, okay? Which in the time domain means that if we have a sinusoidal wave, where we start counting, where is the zero, okay? This is basically what we have, okay? Which are the elements that we have in the circuit? You know that we have resistance, we have capacitors, we have inductors, okay? You know that in a direct current system, we have that the voltage is constant, and the ratio between the current and the voltage is just a scalar, which is the resistance. Okay, everybody knows that, the Ohm's law. What happens when we have alternating currents? Then the voltage is a sinusoidal wave, okay? So it will be the current, and the point is that we can represent these sinusoidal magnitudes by means of these phasors, which, as I introduced, are nothing else than imaginary numbers that are rotating at a given frequency that is determined by the system in which you are. Here, 60 Hertz. In Europe, we have 50 Hertz. The ratio between these two phasors is what we call the impedance. That has a real part, which is the resistance, and an imaginary part, which is the reactance. And why I'm saying that? Because at the end, you see that in the capacitor and in the inductor, the relationship between the current and the voltage is not constant, it's a derivative. When you differentiate a sinusoidal wave, you have another sinusoidal wave with a phase lag of 90 degrees. Okay, it can be lagging or can be leading. So at the end, what we have in a power system is whenever you have a load, and a load could be something with an imaginary part and a real part, both of them can be non-zero. If the voltage is this expression, the current will be the same expression with a different magnitude and a given phase. This phi is the current phase lag with respect to the voltage. Okay, more or less? So instantaneously, if you make the product of the instantaneous voltage and the instantaneous current, you get instantaneous power. So you can imagine that if you have two sinusoidal waves at 60 Hertz, for instance, and you are multiplying instantaneously what is the voltage times the current, you get the instantaneous power. And you can see that this power, in black here, has also a sinusoidal wave, but with double frequency. And you can, well, this is where you have 60 hertz and 50 hertz. The point is that this instantaneous power can be split into components. One that has a non-zero average value, which is what makes active power, which is the part of the power that allows us to move things or to heat or to transform into useful work. And another part which is also a sinusoidal wave with double frequency whose mean value is 0. This is what we call the reactive power. It's something that is occupying the network but is not producing useful power. But it's a consequence of having these kind of loads where you have resistance, capacitors, and inductors, okay? This is how we can transmit power in an AC. This is an analogy, okay? At the end, if we have here the generator is rotating, here we have the motor. It's like we are, we don't have a direct current, we have an alternating, it's going back and forth, but we are able to use this system to extract power in the loads, and depending on what is the phase angle difference, we will be transmitting more or less power. Okay, I'm skipping these concepts, let's say, quite fast, because I guess that most of you are a little bit aware of that. The point is that depending on the phase lag between the current and the voltage, this phi, we will be having more or less active power. You can imagine that if the current is the phase 90 degrees with respect to the voltage, or the current with respect to the voltage, the average value of this product will be 0. If you have a pure capacitor or a pure inductor, you might be consuming current, but at the end of the day, you are not having any average value. Why? Because it absorbs energy, it transforms it in electric field in the case of a capacitor, or in the magnetic field in the case of an inductor, and then it returns it back. So at the average is completely 0. You see what I mean? It's getting the energy and giving it back. So when we have an ideal inductor or an ideal capacitor, we don't have active power, we only have reactive power. What happens in normal occasions? What we have is loads that consume active power, and there are certain loads, typically motors, which are inductive, and this is why we have some consumption of reactive power. Okay, so we have active power and reactive power. What we like to say to our students is that reactive power is nothing else than the consequence of having not a null phase between the currents and the voltages in our power system. Okay, this is a little bit explain what I have just said. These are the phasors representation, and I'm just saying that because we need to express the voltage at every node of my network by means of the magnitude, okay, which is related to how, I mean, what is the amplitude of this sinusoidal wave, okay, and what is the angle with respect to a given reference. Okay. So whenever you have this impedance, the resistance is the real part and the reactance is the imaginary part, we have voltages and currents, and this is the apparent power that has the real part is the active power or real power, and the imaginary part is Q, which is the reactive power. Okay, so what is a typical network? You know that we have three-phase systems, so you don't have a single AC, a single phase system. What we have is three phases. The reason is that if we have three phases with 120 degrees phase between the different voltages in the three lines, if it is symmetrical, the total power that you're transmitting is constant. If you sum these three, let's say, instantaneous magnitude, it's perfectly constant, okay? But when we represent a power system, we are not drawing the three conductors. We are not drawing the three, let's say, wires that connect every substation. So we normally use this kind of single phase diagram. So this is a bus, okay? And this is one line, for instance. This is just an example. This line represents, in fact, there are three circuits because we have three phase systems. What can we have in one of these nodes? We can have a generator, like this symbol, or we can have a demand with this arrow, meaning that we are extracting power. And this is just, well, depending on the topology, you are connecting different nodes with different lines. More or less clear? Yeah? What do we have as well in the network? We have this symbol. Do you know what this symbol is? This is a transformer. We need to transform the voltage, and thanks of having, this is the reason why we have alternating current. It's because we allow us to elevate, to rise, or to reduce the voltage. We rise it when you are producing power in a power plant. Typically, at the outcome of the generator, you may have, 20,000 volts, 20 kilovolts, okay? Why do we want to rise the voltage up to, in Spain, for instance, the high voltage is 400 kilovolts. Why do we rise the voltage so much? As the power is the product times, voltage times the current for a given power, if you increase the voltage, you reduce the current. So the product is the same, but the current, if you rise the voltage, the current is much lower, okay? So the lower the current is, the lower the losses, because whenever you have a current, which is nothing else than number of electric charge per time unit, you have, by the Joule effect, you have losses. So the lower the lower the current, the better, because you're transmitting the same power, but with lower losses. But of course, we cannot have here 400 kilovolts, so we need to then step down the voltage until we have. Okay? What we have here, also here, I don't know if you can see it, these are converters. Why? Because you may have not only high voltage AC current, or AC lines, you may have also HVDC lines, which is nowadays a reality in many systems, especially when you have long distances. Do you know what are the advantages of having HVDC lines connecting different areas? An HVDC line is a line that connects two nodes, but by means of direct current. Okay? This happens, for instance, in Europe. In Denmark, you have one part of the system is, let's say, connected to the Nordic countries, and another part is to the European continental. Well, if you have, and they are not synchronized, which means that you cannot connect them with a transmission line because it's not the same electrical, let's say, area. By means of these links, you are able to connect a synchronous system, because here you have one converter in one side and one converter in the other, and by means of an adequate control, you are able to connect them and transmit power. Okay? Okay, well, this is an example of the topology of the network. We are going to characterize every bus, every node, by means of different magnitudes. Which ones? The active power. This active power that can be either injected by the generator or consumed by a load. I mean, if you have a factory, you are extracting active power. If you have a generator, a hydropower unit, for instance, you are injecting power. But also you have reactive power, and you have consumption of reactive power because, as I said before, if your load is a mixture of inductors, resistance, and capacitors, whenever you feed this load by means of a perfectly sinusoidal wave of voltage, the current will be a sinusoidal wave if we don't have non-linear loads, but the current will not be in phase with the voltage. Okay? It will be a causality that is perfectly aligned. So always you're going to have a certain amount of reactive power being consumed. And the generators are able to control the amount of reactive power that they inject. You know, in a generator, in a synchronous generator, at the end what you have is like a magnet which is rotating, right? This is how we create the voltage. The generator, what does is to get, some mechanical energy in the shaft, rotates this magnet, and it induces some voltage in the windings, And by means of changing the field current, so how big the magnet that is rotating is, you are able to control the voltage at this node and therefore the reactive power that you are injecting or absorbing depending on the control strategy. This means that the generators have the ability not only to control how much active power they inject, but also how much reactive power they inject. And this is why they have active power control and voltage control. You know that these are two main magnitudes that need to be controlled in a power system, because what is the main difference between electricity and other commodities? It's difficult to store. I mean, in the system, thank you, you need to keep constantly a perfect balance between generation and consumption. You cannot store, you always can store something. In a battery, we are storing energy. We are storing electricity, but let's say generally speaking, we cannot store that electricity. So constantly, there are different control loops that are ensuring that always there is a perfect balance between generation and consumption. How does the system operator ensures that this balance is being kept at every time? Any idea? How can the system operator detect that there is a lack of power? Imagine that you go home and all of you start connecting your loads, your micro oven, your loads, but you don't call the supplier, hey, I'm going to connect my appliance. You just connect it automatically. And this I don't know, 500 watts, somebody has to generate it. So if you connect that load, instantaneously, some generator is increasing a little bit its generation to satisfy this load, and you are doing that without warning. How is this possible? Exactly. Theoretically, if you let's say compute the currents and the voltages, you could compute what is the total load, and you could send this signal to the generators. But that's not possible. That's not realistic, because you have losses. Sorry, you have consumption, but you also have losses in the system. So you cannot compute all the individual consumptions, sum them, and send that set point to the generators. What the system does, as was mentioned here, is to detect the frequency. If the frequency of this sinusoidal wave, if it is being reduced, it means that there is a lack of generation in the system. Why? Because a generator is nothing else than, as I said before, a magnet which is rotating with a big, let's say, a mass. It's a big piece of metal, iron, copper, etc., rotating with inertia. If you connect more consumption that is needed, these masses will tend to slow down, okay? And therefore, because you absorb that energy from the kinetical energy which is there, they therefore reduce their speed, and this is directly connected to the frequency that we have in the network. So if the frequency starts to be decreasing, it means that you have a lack of generation, or more demand than generation. It's like if you're riding your bike at constant speed. If somebody jumps in, automatically you will slow down. If you want to keep the same velocity, you need to put more energy in your pedals, right? Or if somebody drops from the bike, you will accelerate. So you need to reduce your torque. Okay. Okay. So also the system at every node has a magnitude of the voltage. The nominal value, the nominal voltage might be 400 kilovolts, but instantaneously you may have 410, 415, or 395. There is a given tolerance where you can have more or less than the nominal value. This is the amplitudes, okay? And also you have a phase angle, which is what I mentioned before, this angle between your voltage and the reference that you established. normally expressed in radians. Okay? So, imagine that you know all these magnitudes. So you know how much power, both real and reactive power, is being consumed in the load buses. Imagine also that you know what is the power and voltage magnitude in the generation buses. The so-called power flow problem is the problem that tries to obtain which are all the voltages in all the nodes, both in terms of the magnitude and angle, in order to compute what are the flows of power in all the transmission lines. And this flow can be both active power and reactive power. This is nothing else than solving a very nonlinear system of equations. It's not obvious. Okay? Here you can see what are the equations that relate all these magnitudes. And it's not obvious to see what are the flows for every line, taking into account the topology of the network and, of course, all the electrical characteristics of the lines. This is just solving a set of equations which is very nonlinear, and this is why there are different methods employed to that, like Gauss-Seidel, Newton-Raphson, etc. What is the OPF, optimal power flow? Is not only that I'm going to take into account this relationship between the magnitudes that I mentioned before, but I have the ability to change the dispatch of some generators, for instance, in order to satisfy the demand while respecting the maximum flows in all the lines. You know that the transmission capacity of a line is not infinite. You have a maximum capacity that you cannot exceed. Why? Why do we have this maximum capacity? Imagine that this is a transmission line. Okay, this is one. I mean the conductor. Here we have some power being the power flow that is flowing here. If you increase the current, the power in this line, the power that is dissipated is I squared times the resistance of this conductor. Okay, so the higher the current, the higher the power flow that you have in the line, the heat dissipated will be increased, and this is going to rise the temperature. What happens with a conductor if you increase the temperature? It expands, right? So the length will be increasing, and therefore the distance here to the ground or to a tree will be lower, and then you may have the risk of having here a short circuit. So this is the thermal capacity of the lines. This is why in winter, as the temperatures are lower, you can transmit more power than in summer, because by the environmental conditions, the temperature is lower, and therefore you can dissipate easily this heat. Okay. So this means it's like there is no physical limit that prevents you from transmitting more power. It's that situation what causes those limits. By the way, as nowadays we need to transmit more and more power, one of the tendencies is to compute the maximum power that you can transmit, measuring what it's called doing the dynamic line rating. So it's not only using a nominal value for the winter or a nominal value for the summer, but taking into account the conditions of this line in this particular situation and conditions. Also depends on the wind. It also depends on many factors. Okay. Okay. The point is that when we optimize the operation of my network and my generators, we need to take into account that the flows of the lines cannot be violated, and therefore we need to compute these previous equations while I'm optimizing. So this is why we call them optimal power flow, where the objective is to determine how much power should be produced by every generator and what voltage should be established as a set point to them in order to minimize a given objective function, typically to minimize the total operational cost, while respecting all the generator's constraints, but also the transmission limits of my system. Today, I'm going to give you we're going to play with a prototype that is what we call a DC OPF, which is it's a common practice in the power system. DC because of direct current. This doesn't mean that we are going to have a direct current. We have an AC system, okay? But we are going to neglect some of the magnitudes and the relationship of those nonlinear equations that I said before. We are going to it's like we are going to treat the problem as if it was a direct current system. What do we have in a direct current system, in a DC system? We only have active power because the concept of reactive power doesn't apply. Reactive power only applies when you have sinusoidal waves and a possible lag between currents and voltages. In a direct current system, we only have constant current and constant voltage, and therefore only we have resistance. So we are going to assume that we are going to neglect the flows of reactive power, and we are going to introduce some mathematical simplifications, as I'm going to explain now, in order to be able to optimize the dispatch of my generators while taking into account the limits of my generators. Well, this is this is a general course, but I want you to know that there is a lot of research nowadays trying to do a OPF while respecting the nonlinear equations of the AC system. This is called AC OPF, and there is a demand because whenever you apply these simplifications that I'm going to explain here, you are not modeling perfectly the relationship between the involved variables. And when you have a big system, you are creating some errors that in some cases is not appropriate. Now, as we have better computation capacities and solving capabilities, we can have this AC OPF being applied. Okay, so we are going to consider the network constraint in contrast to what we played yesterday. In the unit commitment, remember that we played yesterday, I assumed what I called a single node approach. We didn't model the network. It's like everybody was connected to the same node. Remember that we injected and today we are going to consider the network. What are going to be the results today? The power produced by every available generator and the power flows through all the transmission lines. But as we want to optimize the problem using linear programming, we need to introduce some simplifications. One very interesting outcome of this approach of posing the problem as a linear programming approach is that we can use the dual variables of some constraints that have a very interesting economical meaning. You know from Pablo's first session yesterday that whenever we have an optimization problem, we have a minimization of a given objective function, for instance, the total operational cost, subject to a number of different constraints, right? For any of these constraints, you can define the dual variable, okay, or the Lagrange multiplier if you change the sign. Are you familiar with this concept, dual variables of constraints? For those who are not, basically they tell us what is the impact in the objective function if you relax a little bit the right-hand side of the equation of the constraint. It can be inequality or equality, which means in this particular case, one of the equations that we are going to have today is the demand balance equation at every node. In every node, we need to respect that the total power that is arriving to the node has to be equal to the total power that is extracted from the node. I mean, we are not storing electricity, so every hour, in every moment, the total power that is either locally generated and locally consumed, plus all the power that is arriving to the node, minus all the power that is leaving the node, okay? So in that case, we are establishing this demand balance equation for every node, and we could ask ourselves, what would be the impact in the objective function if I increase 1 megawatt the consumption in this node? You see what I mean? It's like the right-hand side term of this balance equation can be interpreted like, what is the impact if we had 1 extra megawatt? What would be the impact in the objective function? This is especially what the dual variable of this constraint is going to tell me. And this can be done for every node in the system, and we can get situations like this. This is a classical example where we see what are the locational marginal prices in the meso electricity market here in the US, where you can see that there is a variety of possible prices. I mean, these prices are obtained as the dual variables of this constraint. For every node of the system, you have this dual variable and tells you what is the price. What you can see here is that there are places where the marginal price is very small compared to others which is very high. Okay? Why? Because extracting 1 megawatt in one node has a cost that is not the same depending on where you are, because you might be congesting some lines that prevent you from using cheap generation and you need to use expensive generators, while in other places you might be, helping the system to be more alleviated, okay? So, like a takeaway, we can formulate the problems using optimization, which is not only good for having the primal variable, so how much should I generate with my generators, but also we can use the dual information that has a lot of, let's say, economical meaning that can be used for things like that to compute prices. By the way, yesterday, as we had to reduce the contents because of the snow. We only had 4 days, not 5. Yesterday, in the unit commitment model, remember that we wrote, we changed the CO2 price, remember? And we saw that if we increase the CO2 price from 20 to 80, a lot of carbon emitters, fossil fuels, were displaced by other more, let's say, carbon-friendly generators. What we were doing somehow was like putting a price to something, and this can be interpreted as the dual variable of a maximum, a cap to the carbon emission. So it's like you have these two approaches. Either you set a price to the carbon, for instance, and you introduce like an additional cost, or you establish a constraint that says that the total emissions have to be lower than a maximum cap. There are the two ways. Even the regulator has these two approaches to put in practice a given, let's say, policy. Okay, so some equations that can be skipped here. Here is node I, node J. Here is the, let's say, electrical characteristics of this line, the reactance and the resistance and the reactance. This is the voltage in one node characterized by the magnitude and by the angle, okay? V for the magnitude and theta for the angles in both extremes. And you can compute what is the apparent power that is flowing from one node to the other by multiplying the voltage times the conjugate of the current. I'm not going to enter into details, but this gives you these nonlinear equations that I mentioned before. That you can see those expressions are very nonlinear because you have the product of the involved variables, like here, the voltages, and also you have the cosine of the angles differences between the different nodes. And this is true for the three conductors of every line. How can we optimize our system in a linear programming approach? Well, we are going to see that today what we're going to do is what I'm saying in this slide. Okay, that is basically what I've been summarizing. I'm going to go directly to here. So first assumption, we are going to assume that the magnitude is pretty much the same everywhere. We know that the magnitude is not 400 kilovolts in every node. As I said before, it can be 5% higher or lower, but we are going to assume that is always constant. Also, we are going to assume that the reactances are much higher than the resistance, which is something that is normally true. Well, it's not normally, but it's always true because we like to use conductors with a very small resistance because this is going to be losses that you are going to have in any case. And also we are going to assume that the angles differences are very small, and therefore the cosine of the phase angles difference can be approximated by 1, and the sine of the phase angle can be approximated directly by the phase angle. Okay, you know that the limit of the sine of x when x tends to 0 is x. So we are getting rid of these, let's say, trigonometrical equations. So if you make the mathematics here, you will see that when we introduce those simplifications, we are not modeling the flows of reactive power. We are assuming that the flows of reactive power is null. This is why we call this approximation as direct current OPF, okay? Because we are neglecting the reactive power. And under this hypothesis, the flows of active power P is just proportional, because these are constants, to the phase angle difference. The higher the phase angle difference between two nodes, the more active power that you are transmitting, okay? What else? Well, in principle, if you take the original expression and you add the power that goes from I to j and the power that goes from j to I, the sum would be like the difference between the power going in opposite directions. That would be the losses. Okay, so all the power that enters one node and doesn't, that is not available in the other extreme has been lost in the process. Well, the losses follow this expression. What is the problem of this expression? That it depends on the cosine of the angles differences. If we assume that the cosine is 1, this term will be null, and therefore we will not have losses at all. But this is not good, because we want to take into account that whenever we transmit power, we have losses in the system. Okay, so just remember that here we have a nonlinear term, because this cosine of angle differences is not linear, but we will see that there are some possibilities to consider them in the solution. One final, because I've been, pretty fast, just to highlight the most important topics so you are not lost, but without entering into details. But here you have what we call a SB, which is the apparent base power. Well, this is because you know that when we have an electric power system, as I said before, we have different level of voltages in all the chain between the generator and the final consumer, right? We have 20 kilovolts, then 400 kilovolts, then we have 220 kilovolts, 66, the different levels. This is not practical. If you want to solve the resulting circuit, it would be very difficult to be working with 400 kilovolts in one part of the circuit, while, 200 volts or 300 volts in another. How do electrical engineers deal with this variety of different voltage levels? We used what we call the per unit system. This is why some of the magnitudes are expressed directly in PU, per unit, which is like you are working in relative terms. So if the voltage is 1, we have to know that if in this segment of the circuit the nominal voltage is 400 kilovolts, it means that the real voltage in this node is 400 kilovolts, because let's say the per unit value is 1. But if the per unit value is 1 in a place where the voltage is 20 kilovolts, it means that the real voltage is 20 kilovolts. You see what I mean? So we can work everything in per unit. And this simplifies a lot the manipulation and the calculations of these electrical systems. This means that how many degrees of freedom do we have? Well, basically in a power system we have voltages, currents, impedances, which is the equivalent to the resistance in direct current circuits, and power, okay? So you have 4 magnitudes, you can fix 2 of them, and the other 2 will be automatically, let's say, determined. So normally, what we establish is the base power, common for the whole system, and then depending on the segment where you are, depending on what is the nominal voltage in your transmission line, you have a different base value for the voltage. And the current and the impedances are automatically determined. So this is why you don't have to be, let's say, confused if you see that the electrical characteristics of the lines are expressed in per unit. These reactance expressed in per unit, which is the same as expressing it in a percent, well, is the way in which we characterize the lines, because we know that we have this per unit system applied. Okay? So if you are using a specialized software to simulate the power system, when you input the data, you don't express the characteristics of the lines in ohms, but you directly expressed in per unit. And I think that with that I have, let's say, tried to summarize, which was not obvious because well, there are a lot of different concepts, but at least for you to understand now the input data that we have in our system. How are we going to formulate the problem? Well, like yesterday, we are going to follow the structure of an optimization problem. We are going to minimize or maximize an objective function. Today, we are going to minimize the total operational cost, subject to constraints that affect every unit and constraints that couple the operation of the units. And this operation that couples the operation of the units, yesterday in the unit commitment, can you give me an example of one constraint that coupled the operation of the different units? Yesterday, in the unit commitment, for instance, it was the demand, because in every hour, the sum of all the power produced by all the generators have to be equal to the demand. So it's not that you can produce whatever you want. If you produce more with one generator, you have to produce less with the other. Everything is coupled. This is what I mean. Here, today, in the transmission economic dispatch problem, or this OPF model, how much I produce with different generators are coupled, not only because of the demand, because of the flows that we have in the lines. As we will see, the flows of the lines is something that depends exclusively on the topology of the lines and the electrical characteristics of the lines. So you, as a system operator, you can determine how much power you inject with the generators and how much power you withdraw with the loads. But the way in which these flows will flow through the lines, as I said yesterday, depend on the 2 Kirchhoff laws. Okay? It's something that you cannot decide. You cannot redirect the power flows as you want. They will flow depending on the nature of this particular system. Okay? So the electrical characteristics of them. And this is why it makes the problem more difficult. Okay? Because you don't have the ability to put a traffic guard saying electrons go that way or no. They will go just because of the electrical characteristics. Okay, so now, as opposed to yesterday, we're going to have a snapshot, one single hour. Of course, these problems can be extended to have multiple hours. As this is let's say a simple model, we're going to have a single hour. And every generator, as we are in the short term, in the very short term, we will assume that we know what is the input data in terms of the unit commitment. Somebody runs the unit commitment and informs us about the generators that are on at this particular moment. So we don't have to worry about the startup cost or the no load cost, so the commitment cost just because you are there. Because today, I'm not able to disconnect the generators. It's there or it's not. is not a decision variable. So in that case today, we are only going to be worried about the, let's say, the marginal cost, the slope of this input-output curve. Okay? When you don't have the ability to disconnect or connect systems, generators, you only have to worry about the marginal cost function. Okay, so what is the data that we have? The demand for every node. Yesterday, we had a demand for every hour. Every hour, remember that we draw the demand function for every hour, and we knew what was the power that has to be consumed every hour. Today we have the same, but the location is important. So we need to know where the loads are located in the network. We know that we have to assume that we know the unit commitment of all my generators. We have this marginal cost, that tells marginal consumption, that tells me how much BTUs per megawatt hour that I'm producing, my generator consumes, the fuel price. Also, another term for the cost is the operational and maintenance cost. We are going to assume that we have a linear expression. Then we have the limits of my generators, maximum and minimum stable load, the gross to net coefficient. Remember yesterday that we said that whenever I produce with my generator, not 100% of this production is injected into the system. Part comes back to the power to feed all its auxiliary services. And what about the water? Because I skipped this slide before. For the water, imagine that we are in an hour. Should I use water in that hour? I mean, should I use a hydro unit by releasing water from the reservoir to supply the demand in this particular hour? Well, what did we do yesterday in the unit commitment? Somebody, a medium-term planning model like the model that Andres explained at the end of yesterday and today's morning, will tell me what is the water value. Yesterday, this water value in the unit commitment was translated into an amount of energy that was available for the week, and we just distributed this available energy in an optimal manner. Now, as we have one single snapshot, 1 hour, if you tell me what is the amount of energy for the hydro system, it means that we are fixing the production. So instead of doing that, I'm going to characterize the water by means of its water value. So it's like if it was another fossil fuel. It's like this is it has no value, but as I said yesterday, it has no cost because it's free. It rains or it snows, but it has a value. The opportunity cost that can be assigned to these hydro resources. Only a model like the medium-term planning model can inform me about what is that value. Okay. So it's going to be considered like any other fuel. Okay. And then we have for the hydro generators the same, the maximum power, and normally this ratio between the net power and the gross power for hydro units is almost 1 because the electrical consumption can be neglected here. Okay, what about the network? Well, it's important that we inform what is the topology of the network. So we need to know what is, I mean, if you want, you can forget about the mathematical formulation here, you get the idea. You need to tell the model where is located every generator, because as we need to establish a balance at every node and to consider all the topology of the transmission lines, we need to tell where the generators and the loads are located and what are the lines that are connecting the different nodes. Of course, only if you have a line, a physical line, you need to consider that the flow in this particular line can be limited. If you have no line, the flow has to be equal to 0, of course. Okay, and for every line connecting nodes I and j, you have the reactance and the resistance, which are those real and imaginary part of the impedance expressed in per unit. And finally, we need to tell what is the maximum power flow in one direction. I mean, if the maximum power flow in that direction from here to here is a given, we can assume that in the opposite direction it will be the same but opposite in sign. Okay? We are going to assume that we have the same limits, although it could be different, especially if you consider other aspects like stability, etc. And we need a base power, which is this magnitude that we need to transform per unit into real values. Okay, so this model that I'm going to play now is going to be the simplest model of the whole course. I mean, it has some, let's say, difficulties in terms of using not so evident magnitudes, these things that I've been explaining here, but from the optimization point of view is very, very simple, okay? What are my decision variables? My quantities. QT is the quantity, so how much power I produce by every T, which is every thermal generator, okay? And QH is how much power I produce with my hydro generator, so the production. But I can have also consumption of pumped storage generators. So B, because in Spain we call it bombeo, okay? B, it is how much power we consume with my pumping storage unit. You know that I can do it, I can store if the prices are low to have it available for later. This is from the generators. Can you give me an example of unit commitment variables that I explained yesterday that are not here? What decision variables had we yesterday for the thermal power plants in the unit commitment? Apart from how much power I produce, any? The ramp was like a constraint that we had to take into account between consecutive hours, but in terms of variables that we were modeling, you as a modeler, the first thing that you have to do is to define what are your decision variables. These are the ones that you want to optimize, okay, to accomplish a given objective. What variables did we have yesterday? Well, these are constraints. It's like, okay, this is a technical characteristic. It is a parameter, but it's not a decision variable. What are my decision variables here? How much power I produce. In every hour, this is a variable, and the model has to determine its optimal value. Yesterday, we had this variable as well, how much power I produced with my generators. And you saw in the figures at the end that they took a different shape because it was the optimal solution. But also we had, as decision variables, the decision to start up one generator in a given hour. Remember, the startup decision was what I wrote here on the screen, the Y, which was the decision of starting up one generator at a particular hour. And you have to define this variable generally, so the model, in principle, doesn't know when it's going to be optimum to start up the unit. You give him the freedom to choose what is the optimal decisions. So when it's optimum to start up the generators, and it's not obvious because in principle you could do it in every hour of the week, okay? But that was a decision that we had to take yesterday. Also, the decision of being on or off the unit commitment was a variable, of course, related to the startup decision, and the decision of shutting down, of course, related to the commitment decision. But they were variables that my model yesterday had to take into account. And this is why we define it as a mixed integer linear programming, because they were discrete decisions, either yes or no. Here, we don't have the unit commitment here. Why? Because we are very close to the real-time delivery. So we are, 1 hour ahead. There is no time to start up. You need to tell me which units are on or off. My only problem here is to determine what is called the economic dispatch, which is another term that we use in power systems, which is very common, that is worried about determining the level of production of my online generator. So you tell me which units are on, I will tell you what is the optimum power that they have to produce. But I have no option to start up one unit which is off because there is no time, okay? In this economic dispatch problem, the marginal cost is the most important thing, okay? Okay, apart from that, as we have included the network here, we have new variables that we didn't have yesterday. We have to model the network. Which are the variables that we are going to need? The phase angles of all my voltages. At every node, I have theta sub I, which means what is the angle in radians at the node I. In every node, you will have a different phase angle. And these are my variables. And the power flows through all the lines. Power flows of active power, because we are neglecting in this DC OPF, we are neglecting the flows of reactive power. And that's all. I mean, they are all my variables. Okay. Yes.
Hopefully I've explained, right, for the first part of the class. What do you mean by phase angle?
Yeah. It's like the voltages at every node is a sinusoidal wave. It has a magnitude, and with respect a given reference, you have an angle. It's like the phase with respect. It's a sine function, which the sine of omega t, where omega is the frequency of the system, minus a given phi, a given angle. And every node has its own angle. In a system, you need to define what is the reference bus where you establish that the phase is 0. And all of them are referred to this reference, okay? Which is equivalent to say what is the time where you start counting. Okay, so let's go to the equations. Well, the demand balance constraint, forget about the formulation if you want. The idea is very simple. All the power that I have in this node that is locally generated, so I'm going to sum all the thermal power of the generators which are located in this particular node I, plus all the power that is generated by hydro generators or minus its possible consumption, plus all the power that is arriving to the node by lines, or minus which is leaving the node to neighboring lines, connected transmission lines, has to be equal to the demand. This is the demand balance equation for every node. But here I'm adding, let's say, an auxiliary variable, which is called non-served power, just in case the problem is infeasible. Sometimes it's not possible to satisfy all the load, because imagine that the lines are congested. There is no way to do that. If we do that, you may have an infeasible problem. So what we do is to add this variable, which is realistic, because in a power system, sometimes the system operator has to do what is called load shedding. In Spanish, deslastre de cargas, which means that we need to disconnect some loads because we are not able to supply them. Okay? Of course, this has to be let's say, a very exceptional solution. So what we will do is to penalize severely this non-served power in the objective function, because otherwise the cheapest cost would be not to satisfy the load. So we need to penalize the non-accomplishment of these loads. Then we have, for every generator, as the unit commitment is an input data, we know what are the limits. They can be the maximum load and the minimum stable load, or could be more restricted if you want to consider RAM constraints with respect to the previous hour, etc. And the same for the hydro generators. And then you have the previously mentioned relationship between the power flow between every line connecting nodes I and J and the phase angles. As you can see, it's a linear relationship, okay? Because there are no more than the product of the phase angle difference times the base power divided by the reactance. In many cases, you may find that the lines are characterized by the admittance, okay? Y is the inverse of the, well, it can be the impedance. You can find the inverse part, the inverse, and well, at the end is electrical characteristics of the lines. and then the limits of the line. So the power flow can go, imagine that is 100 megawatts. The power flow can be negative. What means that the power flow is negative? It means that it's like when you are solving a circuit in high school. It's like you define the current in one direction to be positive. So if the result is negative, it means that in fact it goes in the opposite direction, okay? So here the power, you define it positive when it goes from I to J. So if the value that results from the optimization is negative, it means that in fact it's going from J to I. But we not only establish a limit to the positive, let's say, direction, we also establish a limit to the negative direction. So if in imagine that it's symmetrical, the limit is 100, okay, from here to there, it can travel 100 megawatts maximum. But in the opposite direction can be no lower than minus 100. It cannot be minus 200 because this might be out of the interval of feasible values. Okay. What is the objective function? Well, if you want, I'm just going to explain. We have to minimize what are the fuel costs, what are the operation maintenance costs, and for the hydro generators, I'm computing what is the water value, this is input data, multiplied by the amount of water that I have released. But be careful, because for the pumping, if I decide to pump, I'm not spending a resource, I'm storing this resource. This is why, in that case, I would gain some profit, okay? Knowing that the pumping has a given efficiency. So I know that if I spend 100 megawatts hour, I'm only going to store 70% of this for a posterior use. So it's like, this means that my decision of pumping water has to take into account the efficiency, knowing that this water has a given value. And then we include these non-served power terms, one variable for every node, multiplied by the cost of non-served power. What is the value, the value of this non-served power? This is a tricky issue, because for the generators it's quite easy to determine what is the cost. If you are using gas in a combined cycle power plant, you know what is the price of the gas, you know the efficiency of your generator, but it's quite simple. But what is the cost of not satisfying the demand of a given customer? Well, it depends. Depends on the usage of this electricity. If it is for only leisure, maybe it's not so problematic, but if the loads are really, cannot be interrupted, the cost of this non-supplied energy could be higher, okay? In our case, we are going to assume that we have, for instance, $1,000 per megawatt hour, which is a common value used in the literature. Okay. Questions up to now? Now a few words about these dual variables. For every constraint, as I said before, I'm going to define the dual variable. And the dual variable of the demand balance constraint for every node, this is what I said before. What is the right-hand side term of this equation? Normally when we write an optimization problem, we put all the variable terms on the left and the constant terms on the right. So what is the right-hand side here? The demand of the node. So the dual variable of every constraint, this is formulated for all I. This tells me what is the change in the objective function. The objective function was the total operational cost. What is the change in the objective function if there is a infinitesimal increase in the right-hand side of this equation? So what is the extra cost of having, let's say, 1 extra megawatt of demand in this node? This variable will tell me this impact, okay? When marginal pricing theories, in fact, it was here, Professor Fred Sweppy, they designed the electricity markets and they established the concept of marginal price. at the beginning, to compute these marginal prices, it was necessary to increase the demand, compute the cost, and make the difference with the previous case. And this had to be done for all. But by means of formulating the problem as an optimization problem, automatically you can get all these duals in one single shot, because the result of an optimization problem gives you all the primal variables and all the dual variables of all the constraints. So this is why we can compute easily these dual variables. Yeah?
So you will also get, as a result of any optimization, you get the range in which that dual variable.
Well, it's not a range, in fact. The problem of the dual variables is that it's local information, in the sense that it's like a derivative. It's a derivative.
It's not linear.
Well, the problem can be linear, because here everything is linear. It's a linear programming problem, and therefore all the constraints are linear. But the dual variable is only valid in the solution. Of course, there is a certain range where it doesn't change, but the interpretation of these dual variables is only true in the solution. If you move a lot, or if you move more than a small interval, you cannot assume that this dual variable is going to.
That dual variable interpretation in the real world will be subject to the expert that is reading or interpreting.
Not really. No. I mean, you can compute, for instance, as the example I said before, the dual variable of the demand balance constraint can be used to compute the price of the electricity in this system. But the problem, I mean, the situation is that if the demand changes, or the situation changes, the value of this dual variable needs to be recomputed, because it depends on the solution. It's like depends on the point in your problem that is being solved.
I understand. So maybe comparing to other optimizations that I work on, and whenever they are non-linear, I understand perfectly the concept of having just a point in time marginal cost, which I cannot extrapolate like many units, because I will have it will not be effective, or I will completely lose the point of the context in which I'm using it. So that's why, okay, when this type of problems, it still have the dual variable. So how can I read that? Because it is giving me a marginal unit, and just to give me the opportunity to be able to understand how the whole optimization works when I increment or decrement, depending on what the
I think that I get your point. I mean, you have a dual variable for every constraint. Okay. Every constraint has its dual variable. For instance, I mean, which means what is the change in the objective function if only I change the right-hand side of this particular constraint while keeping the other constant.
Okay, so it's not optimization. It's not to be, because what I use dual variables, or at least marginal costs in all optimization problems, is to be able, okay, if I change this variable that much, how much my optimization value changes.
So there are basically two concepts in optimization. One is marginal derivative or partial derivative for any constraint, and we call that a dual variable. And the other is marginal information for the value of a variable, and this is called reduced cost. So again, is the partial derivative of the objective function with respect to a marginal modification of a certain variable will be called reduced cost, and the marginal information by marginal change in the right-hand side of the constraint will be called dual variable.
Okay.
And for example, the spot price of the electricity, the short-run marginal cost are the dual variables with respect to the balance between generation and demand constraint.
Okay, thank you so much.
I'm going to use in the second part now. We are going to have a break, and in the second part we are going to play with the prototype, and I will show you the duals. I think that we have the opportunity to discuss it further. But before the break, just let me give you a couple of extra concepts. As I said before, we have this loss expression here, which is nonlinear. One possibility is to assume that we are able to compute these losses and consider that whenever we have a line, we assign half of the losses of the line to the extremes of the lines, like extra let's say, extra load. So the model will prefer solutions that give place to lower losses because it's energy that has to be produced. You see what I mean? So if we could compute these losses according to that expression, we could assign half of the losses to the extremes and include them in the load balance equation of every node. What is the problem? The problem is that this expression is nonlinear. One possibility could be to make many cuts, okay? Approximate this function by the simultaneous consideration of all these cuts simultaneously, saying that the losses have to be greater than the simultaneous region defined by all these cuts simultaneously, okay? This is one possibility. That is the one that is implemented in the prototype that I'm going to present. If you are using quadratic programming, you can make the Taylor expression of that and get rid of the terms higher than the second degree and can be approximated by a quadratic function. And you don't need to introduce the cuts. You can solve the problem directly using quadratic programming, okay? But in the case of today, as I'm going to use hikes as yesterday in Google Collaborate, we needed to use this linear expression, okay? So we are going to consider the losses. Why? Because if you are very far, if your generator is very far from the consumption, I mean, the cost of asking for an extra megawatt of power is not the same, the impact of this extra megawatt if you are very close to the generator, because if you're very far, it means that the power has to travel a lot from the lines, through the lines, and therefore will induce more losses. So the cost will be not the same because you will have higher losses, okay? Even in the case of not having any congested line. Okay, so let's make now a break. I think that we are just 5 minutes. Well, I think that we are okay. We can start at 11. Is it okay? Yeah, like 10 minutes break. And I don't know if we can take it, because yesterday we didn't took a picture of the whole group. You saw in Andres' presentation that we like to have a memory of. Would you mind if we take a group picture just for our, let's say, for our history? So let's make the picture and have a break of 10 minutes. Thank you. Yo creo que sí, ¿no? Porque si no se nos va. Sí. If you're ready, we can continue because we have, I mean, we need to finish at 11:30, if I'm not wrong, to the next speaker. So, if you go to Canvas, here, session, the network as a backbone, here are the slides, and here you have two prototypes. I hope that we can use both of them. I'm going to start with the prototype in Python Payomo, so you don't need to install anything. So we are going to repeat something similar to what Andres did before. And here in the slides, you have the instructions for prototype 1 and for prototype 2. The first one is this one. So first thing that you have to do is to download this zip file in your, let's say, in your local directory, in C, whatever you want, and extract all its content. Okay? I'm going to do it together with you. So I press here, I download the file. I'm going to copy it. I'm going to use a, I don't know, in a temporary file. New. Sorry. So we've just started, so you haven't missed. So I'm just saying that you need to go to Canvas and download this file. okay? The prototype DC OPF in Python Payomo. So you download it and you extract it to a temporal working directory. So extraer todo. Okay, so here I have my files. You have input, output, and 2 files. Next thing, you need to access Google Colab link and then click on code. And when you click on code, you need to write this. It's like what Andres was saying before. You need to mount the drive. So I'm going to Google Colab. When you are in Google Colab, you need to write code, okay, here. So we have this cell here, so we paste here the code that I need to run. I'm going to run it. Something is going wrong, sorry. Oh, yes, be careful the spaces when I paste it. Import drive from Google. Be careful because I just copy paste what is here. Google.colab from Google.colab import drive, está bien. Drive mount content drive. Be careful because if you paste it, you need to make sure that the commas are okay. So you need to then continue. This is like you are permitting Google Drive to connect to the. So be careful because if you paste it from the PDF, this is a apostrophe. I don't know if you just copy it, or you can write it directly if you want. Maybe it's easier. Okay, everybody was able to run it successfully? Who couldn't? Well, once that you have this done, you have to go here to files, because now we are going to upload the files. So you have here the expressions. So we are going to upload the model, but in the My Drive, here, Drive, here you have My Drive. I'm going to create, well, in fact, I have created because I'm going to delete this one. Let me see, delete folder. So I do the same as you. Okay, well, let me do another thing. I need to rename it. So let me be clear. You are in my drive, so create a new folder, and call it DC OPF, and try to keep this name because it's necessary for the code to work. DC underscore OPF. That will be an empty folder. Okay? Once that you are there, you need to create two subfolders here. So here, new folder, one is called input, and another one, new folder, which is called output. Okay? It's a very simple structure. Okay. Next step. From the folder, from the let's say, local directory that you have, you are going to drag and drop the two Python files to the DCOPF. Okay, to the root. To DCOPF, you need to have the DCOPF.py and create fig DCOPF.py. Okay, and then, this is just the last, go to the input file and copy all the files here, drag it into the input. The output is just a folder that you need it to see the results, but at this stage, you don't need to do anything else. So I'm going to copy all the input files that are CSV files. Okay, now that we have this, we are going to do the same as Andres did before. We are going to click on code, and we are going to run the model. So code, we have a new cell, and we paste this, in principle. Let me see if it works. And we run it. Let me see if it works. Yes, it seems it's working. So if you go now to the output folder, you should have something in it. Like here, I have all these files in the output because the model has worked. So I want you to see if that's the case. So if you have this information where you have what are the dual variables of the demand balance. If you check here, you have the dual variables. You have the variables, for instance, which are the power flows in all the lines. You have the thetas, the angles in all the, here you put, for instance, 25. You have for any of the 9 nodes. So now I'm going to explain the details, but first of all, I want to know if any of you were able to run the model. Let me open this figure, and I'm going to explain what it has. Okay, so here we have an illustrative example with only 9 nodes. This is the topology of the network that we have optimized. We have several generators. Some of them are thermal in nodes 1 and 2 and 9, and we have and we have hydro generators in nodes 3 and 4, and a pumped storage in node 3. In these input files, you have all the electrical characteristics of the lines and the costs of every generator, and we have solved the problem. Now I'm going to see how the problem was solved, because one of the ideas of this course is that you get familiar with the coding, but I want you to interpret these results. Here, the solution of the problem has determined what is the optimal production of all the generators. So we see here that the total generation of the 3 generators there is 0.987. In node 2, they have 1.213. So in this purple is the total nodal generation. The model itself contains what is the individual production of every generator. And here I'm just showing the total value, okay? Also, it is telling me what is the demand at every node. In this node, we have 0.5 gigawatts and so on, okay? So this is input data. The production is a result of our model. And here in green, what it shows is what are the power flows through all the lines in the optimum. This is an example, and whenever I'm congesting one line, the flow is going to be shown in red. So can you see what are the line that is congested in this example? The line that connects node 3 with node 5, as you can see here, it's working at 0.5 gigawatts, so it's 500 megawatts, and it's the maximum capacity of the lines. So this means that all the other lines are, let's say, within its limits, but this one is what we call in optimization is a binding constraint. It's a constraint that is changing the solution. It's affecting the solution. Because my question is, when we formulated this optimization problem, I imposed that the flows in all the other lines had to be within their limits. But if this is the solution, what if I remove the limit constraint of, for instance, the line that connects 1 and 4? The optimal solution is 0.292, okay? And the limit of this line was 0.5. If I remove this constraint, do you think that is going to change the solution of this problem? If you tell me that I cannot move farther than this wall, and in the optimum I'm here, do you think that if you tell me that I cannot move farther than that wall, I'm going to change my optimal solution, which is being here? For that specific line. So what I mean is that if you have a constraint that is not active, if the wall is there and I have to be from the wall to the right, and I'm here in the optimum, if you remove the wall, I'm still going to be here. So you can remove the wall, and this is not going to change the solution. So when you have a non-active constraint, you can remove it, and the solution will not change in this particular case. You see what I mean? However, if you tell Javier you cannot move farther than the wall, and in the optimum I'm here, if you leave that the wall is 10 centimeters to my left, probably if I want to go in that direction is because my optimum maybe is in the yard. I prefer to be there. So I will move a little bit. You see what I mean? So the dual variable of this constraint tells me how much the optimal solution improves if you give me a little bit of more flexibility. Okay? In that case, if in the optimum I'm here, if you leave me to go 10 centimeters to the left, the solution will not change. The dual variable of this constraint has to be 0. So when the constraint is not active, the dual variable has to be 0 because it doesn't change at all the solution. However, in this case, if this line is congested, if we allow the flows of this particular line to be, higher, probably it will be able to use cheaper generators, and therefore it's going to improve the total cost. You see the idea of the concept of the dual variables of the constraints, the units, sorry, the constraints that are active, the ones that are not active, or binding constraints. Everything is related. Okay? What else? Here, the model is telling me what is the marginal cost of the node, so the locational marginal cost, which can be used to determine prices in an electricity market. Here, for instance, in node 7, I have this value, 49.394, which means that if I extract 1 megawatt here, the cost would be increasing 49 euros per megawatt hour of extra demand. And you see that these values are different. For instance, in this place, in the node 3, the marginal cost is 28. Why? Well, you can see the input data. That is the water value of the hydro generators which are there. So depending on where you are in the node, asking for an extra megawatt will have a different impact on the total cost. And this is why we build the prices in the electricity markets using these dual variables, because they provide a good economic signal in the sense that if we have in this place, for instance, very high prices, if you are a producer, where would you prefer to install your generator? Well, if this is the price that they are going to pay me, where do you prefer to install your generator? Here, where the price is 49, or there, where the price is 28? If you are a seller, where do you prefer to install your generator? Here, okay? However, if you are a factory, where would you place your factory? Where the prices are lower, right? So they provide right incentives for connecting additional generation competitive, so with lower price. If you connect here a very expensive generator, you are not going to change anything. But if you install here a cheaper generator, you're going to displace this expensive power here. And therefore, it provides a good economic signal to lead optimal investment. So locational marginal prices is not only an operational issue to determine how much should I pay to the generators or how much should I charge to the consumers, but also it provides a good investment signal to the system. Okay? Questions? Any question? Let's do a little change here. I'm going to open the code. Yeah.
What you're looking at here, it's just one timestamp.
Yeah, of course. This is like one single hour. It's one snapshot. Yeah. I mean, everything that I was saying was, I mean, of course, you cannot make an optimal decision in terms of investment just looking 1 hour. You have to do that for 20 years, knowing different. But the idea is that, exactly, yeah. So open the DC OPF file, okay? So here is the code that you can see here. I mean, it's Python Payomo. As you can see here, I have my variables, the angles, B, the pumped storage production, non-self power, Qs, the losses. This is the objective function. This is the demand. So I think that it's quite easy to understand how the model is coded, okay? And I want you to change at the beginning. Here you have these two flags. In the default case, I have considered the maximum limits of the lines, and I have considered the losses, okay? I'm going to remove both of them. For instance, start removing the limits of the lines. Just changing here, instead of true, let's put it false. Okay? So now I'm going to consider losses, but not the limits of the flow. So the resulting solution might be infeasible in terms of, but just to do the experiment. Let's see what happens. I'm going to run it. I run it, pressing this here. Okay. By the way, here in the solution, it tells me what is the flows in all the lines, and also I'm telling you, once that I compute the solution, what is the mismatch between the losses that the model is considering, because it's using this tangent cuts approximation with respect to the actual losses. And now we have a new figure in the output. We have, yes, I'm considering flows, yes, I'm considering losses. But now I have no, I don't consider limit flows, and yes, I'm considering losses. So I have this new result, okay? A new figure. If we see this figure, you see, now the solution has this line which is above the maximum limit that was 0.5. So it's in red because compared to the input data is exceeding the limit, which is, I mean, it's normal because we have removed that constraint from the model, okay? But what do we see here is that despite not having any congested line because the model is not considering the limits, we have different marginal costs throughout the whole system, okay? Because we are modeling the losses. So extracting 1 extra megawatt here is more expensive than extracting one megawatt, I don't know, in these other nodes, okay? Because this power has to travel through all the lines, and they incur in the losses, and therefore, even not considering transmission maximum limits, you may have different marginal costs, okay? But if you don't consider the losses, and this would be my last experiment, if I put here false for the losses, in that case, the result would be like what we did yesterday. It would be a single node approach because we are not modeling losses, we are not modeling the network, and therefore we should obtain a single marginal cost all over the places because the model asking for 1 extra megawatt might not have any impact on the solution, okay? Depending on where you are. So we have now a new figure automatically generated, which is no flows, no losses, okay? So if I open, as you can see here, 40, 40, 40, everywhere this this marginal cost is the same because we are not modeling the losses and we are not modeling the limits, yes?
These matches are related to the active power losses, then to take into account the reactive power losses, we'll have to include like an error, like an uncertainty, or how?
Okay, no, the point is the following. In this model, I'm only modeling in a simplified manner the losses. The losses are only active power. There are no losses of the losses in the terms that active power that has to be generated. In this formulation, we are not modeling reactive power at all, okay? So if you have an AC OPF where you model the flows of reactive power, it's true that the flows of reactive power at the end is the component of the current which is phased 90 degrees without respect to the voltages. And these currents flow through the network and they produces losses due to these flows of reactive power. These losses can be also taken into account, but in that case has to be done with a nonlinear model. That is much more difficult to be solved, especially for large systems, okay?
So in reality, like how negligible are the losses? Do they use like a nonlinear?
One of the task forces in the FERC, like I said yesterday, was let's try to do AC OPFs in order to avoid neglecting these kind of things. Because up to now, most of the electricity markets are cleared here in the US using this DC OPF approximation. But it's not perfect. As you can see, there are things that might have an effect. Depending on the configuration of the system, on the particularities, these mismatches can be higher or lower, okay? In general, let's say the flows of reactive power could be, I don't know, 10% of the actual flow, so it's limited. But depending on the situation, it can be higher. Okay, so I think that now I need to lead the floor to Rory. Just before, while he joins, you have in Canvas a GAMS code example that you can download it now that you have installed GAMS. This is the OPF if you download it. You can simply run it, okay? And you see that it's the same solution. Here you have the GAMS code, okay? It's very simple. Please go ahead. Just while you come. Yeah.
Do you have like detail how did you determine the cost? How did you determine the cost? How did you know?
Well, the marginal cost is just the dual variable of the constraint. So it's a result of the model. So the solution provides you with the optimal solution and provides all the dual variables. I'm just reading the dual variable. I'm not computing anything. I'm just reading the dual variable. In GAMS, here, I'm sorry, but they asked me this. In the GDX file that you have, for instance, here, the demand balance equation, if you run it from GAMS, you have that in every node, I'm satisfying the demand, and it's telling me the solution, the marginal information. This marginal is the dual variable of this constraint, and they are the marginal cost that I'm showing you in the previous slide. So it's just reading the dual variable. I'm not computing anything. Okay? If you want, we can discuss it afterwards. Okay?